This is an example of solving for the hybrid pi circuit. So typically you want to find Rn, Rout, and the gain Vout over Vsig, or the V input. In this case, the input is Vsig. So let's start with the Rn. So to find Rn, you ignore the input the input source, and you're going to take the node pathway to ground. So here, as we come in, we can go two different routes to get to ground. So we can use the resistance reflection rule to remove or ignore this current source, and in order to do that, we are actually located, because we're trying to find the node at the emitter side. So we're going to divide these resistors by beta plus 1, which is going to give us the effect from this dependent current source without having to analyze the whole test source on this node. And we can now, by inspection, say what Rn is. So Rn is the pathway from here, and it only has one pathway now to ground, which is going to mean it's going to be the summation of all of those resistors. So R pi 1 plus R2 plus R1 all over beta plus 1. And that would be our value for Rn. For Rout, again, you have the split pathways. So for Rout here, you have a pathway down here, a pathway here, and a pathway here. So again, we can ignore this pathway if we take the effect of it and reflect it. Again, we're on the emitter node, so we're going to divide the base resistances by beta plus 1. Always remember that our pi is considered a base resistance. So in this case, we have R7 in parallel with this branch. As I come in, these have a summation through there, and then I have a split again, but I notice that on the top of this, if you recall, the equivalent resistance looked like an open for that one. So my total Rout is going to be R7 in parallel with the summation of all of those. So R pi 2 plus R pi, or R4 plus R5 all over beta plus 1. So that would be my value for Rout. Now we want to look at the voltages. And so now we want to find our Vout over Vsig. So to do that, we're going to write an equation for Vout. Again, we can ignore this if we reflect. And now when we're finding voltages, remember that for voltages, so for analyzing voltages, your location is going to be considered where your source is. So in this case, if we're reflecting this transistor, to get rid of this one, this is going to be my location, which is at the base side of this one. So I'm going to multiply R7 to ignore the effect from this one. So if I do that, I can see that I can do a current divider and find the current here, multiply it by R7 to get Vout. So that circuit would actually look like this. We can also analyze it a different way if we wanted to take the equivalent resistance at this node, find the voltage here, and then do a voltage divider with that resistance. So either way, a current divider, current times resistance, or take a full equivalent resistance here at the base of all of these and take current times those resistances to get that voltage, and then from there do a voltage divider again. So we can do both of those to give you practice with both. So I'm just going to redraw that circuit down here. So here's that part of that circuit. Alright, and so from here we can take get rid of this RN. Okay, there's the rest of that circuit and the rest of that side of the circuit. So from this we can do, let's first do the current divider. So the current divider is going to be, the current is going in this direction, which means it would actually be flowing up, but since it's not and we would need it to go down as a plus to minus, this is going to be a negative. Negative GM1 V pi 1 times the branch opposite would be R4 plus R5 plus R pi 2 plus the R7 times beta plus 1. So this would be your current, and I would multiply it by R7. The other way we could solve this would be to combine all the resistances as one resistor here, which means that there would be a pathway here and a pathway here to go to ground. So this pathway would be in parallel to this pathway. So that R equivalent there would be R4 in parallel with R5 plus R pi 2 plus R7 times beta plus 1. And now it would be the voltage we could call Vx would be Vx would be equal to a minus GM1 V pi 1 times that R equivalent. Now that's going to be the voltage just at Vx, and then in order to get the voltage at V naught, we would have to do another divider. So V out would actually be the division of Vx to R7 beta plus 1 all over R7 times beta plus 1 plus R pi 2 plus V5, R5. So that would be another way to get V out. So the other value we would need to get is V pi 1. And to get V pi 1, I'm going to erase these for a minute. So from this one, we're going to find V pi 1, and again we want to ignore that dependent current source. So again, we're going to be at the source location. So that is the emitter side. So again, we would do over beta plus 1. And then this would just be a voltage divider. And so we would have V pi 1 would be a minus V sig. Times this over the summation of all of them. So those would be our equations, and with the known values of the resistances, and then R pi and beta and GM are gotten from the DC analysis, where you can find R pi is equal to IB over VT, and GM so I said that wrong, VT over IB, so V over R, and GM is IC over VT. And then they're related to each other by GM, and beta is GM is equal to beta over R pi. So make sure you also memorize those equations.